All right, I'd like to go ahead and introduce our first speaker today. So Joe Stein is a principal consultant with Big Data Open Source Security. He is a Kafka committer and PMC member. Joe's going to speak to you about real-time distributed and reactive systems with Kafka today. So with that, turn it over to Joe. Thank you.
Can everybody hear me okay? Whoops. Hello? Great, awesome. All right. All right, so quick about myself. My name is Joe Stein. I'm a developer and architect by trade. I built lots of different systems, most notably one that supported like 6 billion mobile devices in production, analyzing like 85% of the world's mobile traffic. About 2 years ago, I started a consulting company called Big Data Open Source Security. We work with systems like Storm and Accumulo and Kafka and Mesos and Hadoop and Cassandra, basically working with our clients to come up with like the glue that takes all these open source systems and integrate them into their infrastructure. We actually just started a new company called Elodina that I'm the CEO of. Consulting is great. We're still going to be doing that, but we're also going to get more into the ISV world. We built a lot of open source software in Go, so you can do pretty much everything you could do in the JVM with Kafka and Go. We're going to start supporting and maintaining that, and then running some software as a service businesses as well. I'm an Apache Kafka committer and PMC member, so I've been involved with the Apache Kafka project for, I guess, like 4 years now. I also have a blog and podcast online, so if anyone's interested in Hadoop, I'm all things Hadoop online. All right, so for this talk, I'm going to kind of just give the, what is a real-time distributed reactive system. It's a lot of buzzwords, so I kind of want to make sure we're all on the same page. I'm going to give a quick intro to Apache Kafka because I don't know how many people in here actually know Kafka. How many people in here are are using Kafka in production? That's not so bad. All right, how many people have actually heard of Kafka? All right, cool. All right, I'm also going to give a quick intro to Apache Mesos. Apache Mesos is kind of fundamental in what we're going to be talking about, but so I want to at least, in case folks don't know what Mesos is, we'll talk about that. I'm going to talk about Kafka and Mesos. And then we're going to start getting into the Accumulo pieces. Once you kind of understand what we're talking about, kind of help to explain where Accumulo comes in and where are some of the benefits of using Accumulo in this type of architecture. And then I'm going to come back to the real-time distributed reactive systems again and get a little bit deeper. And then a little bit more about Accumulo. Okay, so real-time distributed reactive systems. I mean, it pretty much is what it says, right? So reactive systems, asynchronous processing to remove all the back pressure from the data flow. You see reactive systems a lot in JavaScript browsers and all of that, and that's fantastic. But when you lump that into a distributed system, you actually get some very interesting solutions that you can build from it. You could actually process the response of a request that comes in concurrently, right? So you could actually have multiple different systems that have nothing to do with each other, simultaneously processing the requests that came in, and all of them influencing the result for that response, right? So you can imagine a request comes in, some fraud check gets applied, some compliance check gets applied, some inventory check gets applied, and instead of doing these sequentially, you could do them concurrently on different systems, and then those different systems themselves could do them in parallel. So here's a picture of it. So in step one, right, you basically have a request coming in, right? So that's coming into your producers. It might be an HTTP request. It might be an email. Could be any piece of data. Could be an ATM transaction, whatever. Swiping a credit card, doesn't matter. After the data comes into, the producer, it gets put onto the Kafka cluster. Once on the Kafka cluster, you can basically have lots of different consumers reading that data. The entire round trip from the consumer being able to see the data and the producer writing it is about 3 milliseconds at its highest. Just so everyone knows, we're talking about, kind of low-level latency here. We're not talking about microseconds or nanoseconds, right? We're not doing high-frequency trading, but we are talking about something that, a human can't notice. So you can put the system in between, a human and a browser, behind the browser, so that just real-time internet transactions can go through this. Once the consumer gets it, you basically have complex event processing systems that can take this data and do any type of processing that you want on it. Okay, you can use Storm, you can use Spark, you can build your own event processing system. It's kind of up to you. But you could actually now take this data, run machine learning algorithms on it, do compliance checks, have it within the entire distributed system, make all these different calculations, and when they're done, right, the complex event processing system will actually aggregate all those results for you, and then the results, the response that's going back, becomes an RPC call directly back to the producer. So you're looking at about, depending on your workload, right? I mean, you're looking at about 7 to 15 milliseconds total latency end to end. And what you basically have is a system that is completely decoupled from the data and the processing that's happening on it, right? So you can have emails coming in, ATM transactions, whatever data is coming through your data pipeline, and at any time, lump some other processing system on top of it. Additional fraud check, right? It goes live, right? Well, you just have to update the complex event processing system. No other part of your infrastructure has to get updated. So there's a lot of benefits here. And of course, the producer sends back the response. So any questions? Because this is kind of a fundamental piece of the talk. I mean, I think if you're lost at this point, let's quickly talk about it and try to get unlost, because the rest of the talk may not make a lot of sense. Any questions about what we're talking about? If anyone has any questions, feel free at any time to. Great. Yeah, so the question was, where is the producer sending back to? So it depends on how the producer was getting the message to begin with. So let's say it was a HTTP call, and the producer is inside of an HTTP server, right? So in this scenario, the request would be 1, and the calculated response that would go back on the HTTP response would be 7. Now, if let's say it was an email, right? The producer would have the email, and the response back would be the relay to continue sending that email, or not, because maybe you shouldn't, right? That's the whole point, right? So whatever that 1 in 7 is, whatever transmission is occurring for whatever mode of data transfer is happening, wherever the producer is embedded in.
Why do we need to concentrate after the producer and getting
Say the question again?
See that producer over there, why do we need the message from the upstream to go over there?
Yeah, I mean, if you have to do hundreds of different calculations on that piece of data, you need to do that in a distributed system, right? You may need 100 servers to do that calculation, and when the result of that 100 servers comes in, you want the result of that to then go back to the producer. That one producer, that poor little web server, doesn't have machine learning algorithms built into it. It doesn't have all this complexity to do all the processing. Fraud checks, compliance checks. There are all these other different systems that are littered in data centers that you want to have the message, right? So this is a way to basically get the message to those different systems, and after they've made their decision and influenced the result, the producer can now get that result back. Okay, so let's quick about Apache Kafka. Yep, sorry. No, it's okay. No apologies. Yep. Number 6, yeah. So number 6 is where it joins back the message from the original sending, right? Because if you can imagine, you've got 10,000 requests per second per server, or whatever it is, right? This is just that one request. Looks up sends it back. Okay, so Apache Kafka is a high throughput distributed messaging system. It was originally open sourced by LinkedIn back in 2011. There's a bunch of links here. This way, if you're really interested, you can go check it out. Kafkas are all about producers, consumers, and brokers. It's a little bit different than typical messaging systems like RabbitMQ or others that you might find. Producers push data, so they do this either through batching. They have the ability to compress the data. They can do both sync and async operations. This slide's actually a little old. The new Java producer only does async, but that's okay. There's replication built in, so Kafka has some very good, strong durability guaretees. A lot of folks actually use Kafka now as their upfront layer of, hey, we've got it. And they'll actually do things like data center replication for their downstream stores afterwards. Consumers pull. This is very different than most typical messaging systems. A lot of messaging systems are bottlenecked by having to push their data to their consumers. But consumers pull, there's no state held on the broker when it comes to the consumers actually reading. It makes it immensely scalable, right? To be able to have consumers just at any point just go and pull from wherever they want in the stream. And they manage all their state themselves. It also supports zero copy if you're familiar with Java NIO file channel. It uses a transfer to function so that all of the data actually gets copied through kernel space. This basically means that when you're consuming from Kafka, if it was just produced, the page cache will actually store, just natural page cache, it just does this. The operating system will actually store that file that was written in memory. And when you consume the data, since you're going over a file channel, you actually go straight from memory to socket when you're pulling it over. So you're basically getting like a memory to memory transfer. Your bottleneck is essentially your network. So it's a huge performance gain. And messages stay on disk, right? So in other messaging and queuing systems, they're a queue, you pop, it's gone. With Kafka, that doesn't happen. The messages stay there for as long as you want. They could stay there also with different business logic as well. Kafka decouples data pipelines, right? So Kafka is all about removing and separating producers and consumers from having to know about each other, right? So some very typical use cases for Kafka are actually reading and writing to Kafka, right? So your monitoring and graph system, every system has metrics, right? And they may all have them in different formats. So you could actually have all of your apps writing their metrics to Kafka, and then if there's any transformation or translation required before it gets to the monitoring and graph system, you could read that from Kafka, do the transformation, and write it back to Kafka. So some very typical use cases is using Kafka as this log essentially and an intermediary for reading and writing data continuously. Any Kafka questions? I'll be here next 2 days. If you have real Kafka questions that take longer than 10 seconds, we could talk later. But any other questions? No. Yep. I don't know. Better than Voldemort. Sorry. Yeah, I don't know. I never asked Jay, or I think they just want to do that. Yeah.
We can see the low latency requirements, about 3 milliseconds. Is it also high throughput?
Yeah. Yeah. So your bottleneck really is your network. So the question was low latency. 3 milliseconds, great. How about throughput, right? Because if you only put one message in a second, then who cares, right? So yeah, I mean, a Kafka broker, you're looking at 400,000 or 500,000 messages per second, like with a single producer, without any additional latency. Again, your bottleneck is essentially going to be the data going over your network, ultimately. And there's a lot of client libraries for Kafka. So Kafka doesn't have any specific, Thrift or Avro or protobuffer. We have our own custom wire protocol. So everything is just bytes. So this allows us to kind of get real down and dirty with the data and do exactly what we want with it when we want with it. There's a whole bunch of client libraries that people have built, so you can kind of do anything you want with Kafka. There's a whole lot more, Erlang and everything now. We've got 2 quick starts, so if you're interested in checking out Kafka, you can go to our GitHub, check out Scala, Go's awesome. Go check that out. I'll post these slides to my SlideShare afterwards and tweet it out if you want to take a look, or I think they're going to circulate them. Okay, so Apache Mesos. Okay, so quick about Apache Mesos, and it's important for us to talk about Mesos because ultimately when we're building these distributed and reactive systems, we want them to do things like scaling up when more traffic comes in automatically, right? So Apache Mesos allows us to do that type of stuff. The origins of Apache Mesos, if you like papers, these are 3 good ones. The first one is from Berkeley, second one's from Google, and the third one's from Google. The second one from Google only recently got released. Until then it was just, talked about, but now there's actually a paper about how Google does their computing, which is really great. But for the last 4 or 5 years, there's been an open source software package called Mesos that solves the static partitioning problem. So static partitioning, this is what everyone's data center looks like when you're not using Mesos. Basically what you do is you decide, orange are our database servers, and that cyan, teal is, our Hadoop cluster, and reds are web servers, and that yellow is monitoring, and, purple is something else. Right? You basically sit there and you say, I've got, Web 1, DB1, DB2, Web 3, Web 4, Hadoop data node 6, right? You're as a human, you're deciding what software applications should run on every single computer. And what you've done is just wasted a lot of money, okay? You've also wasted a lot of resources because the workloads and the patterns of these different jobs, you don't understand them. You're not in the computer, you're not able to see what's happening and make changes dynamically. So what you ultimately get is something on the left where you've got, when the sun is over the Pacific, your Hadoop jobs are off. Well, that's horrible because when the sun is over the Pacific, that's when everyone's traffic is the lowest. That's when you want to be doing your offline stuff. With Mesos, what you basically have is you don't have that, right? You have the graph on the right where you're able to completely utilize, possibly up to 100% the utilization of your servers. I've heard some good stories about folks that they actually do get things like true 100% utilization through their WAN and on their servers. It's actually quite impressive. So what is Mesos, right? So Mesos is an operating system for your data center. I was originally not going to talk about Mesos in this talk, but because who talks about their operating system, right? And I was like, oh, it's just Linux. But this is a little different because in order for the system to really work, you kind of have to use Mesos. So I felt it important to talk about it. And Mesos is essentially the kernel for your data center, right? What Mesos does is it completely abstracts the resource scheduling and the execution of tasks from the hardware underneath. So if you have 1,000 servers and each have 20 core, right? And let's say 20 gigs of RAM, you now actually have a computer that's 20,000 CPU and 20,000 gigabytes, right? And your applications don't know, or you as a human don't necessarily know where your application is going to reside. You could have an Oracle database and a web server running on the same node. It's completely possible. Now, if you didn't want to do that, there's ways to control that. So there's all sorts of bells and whistles. So the way that Mesos works, the Mesos master, if people are familiar with Yarn, it's actually kind of very different than Yarn. So if you know Yarn, pay attention. So your framework basically is a scheduler and executor. And the scheduler is able to make decisions about how to actually launch the tasks, right? It knows about the nuances of the application so that it can effectively manage failure scenarios, scaling scenarios, what have you. The framework gets these offers from the slaves. The slaves say, hey, I've got some CPU and memory and some disk. And the framework goes, I want it. So what it does is the framework then launches a task. The Mesos master finds the slave that is able to run it. And the slave goes ahead and executes the task. Mesos is scalable to thousands of nodes, right? So it's been running Twitter in production for many years now. If everyone's ever used Twitter before and had to experience the fail whale, this is one of the reasons there's no more fail whale. It's fault tolerant and replicated master slaves, and it uses Zookeeper. This is more of a by the way than a just so you know that you're going to have to use Zookeeper, but I think most folks in this room are okay with that. There's also support for Docker containers. Besides Docker containers, it also has native isolation with Linux containers using cgroups. This way you actually have true isolation between your CPU and RAM for the tasks that are running on a computer. Multi-resource scheduling, so you could do memory, CPU, disk, and ports. We're actually working on some code with some router folks to do some networking stuff as well. And then there's bindings for Python and Java and Scala and Go, so you could actually build frameworks and yada yada. Oops. All right. So let's quick talk about Kafka on Mesos. We've been running Kafka on Mesos for a while now, but we took all that experience of Kafka not on Mesos and Kafka on Mesos, and we developed Kafka on Mesos. So it's a framework for Kafka that allows you to run Kafka brokers on Mesos. A lot of the issues, if you've ever run Kafka before and having to start and stop brokers and reassign partitions, all of that operational overhead has been kind of trivialized inside of the CLI now. So besides all the cool benefit of being able to, auto scale and automatically spin up more brokers because you've got more traffic coming in and you don't even have to touch it, it's automatic. Besides those nice features, we've really spent time to make sure that operationalizing Kafka is just a lot easier on Mesos as well. So Accumulo and Mesos, if I had written this slide 16 minutes ago, I guess there is a framework that someone wrote that's in this conference that maybe we'll get open source, which would be cool. But that's OK. Don't worry about it. You can run Accumulo on Marathon. It works actually totally fine. Marathon is kind of like the initd for Mesos, right? It allows you to start and stop services. Kafka kind of needs its own framework because of some of the intricacies of what it does with replication and how the brokers work because it holds data. With Accumulo, since everything is HDFS, it's a little different. So you really can run it on Marathon, but having a framework would be awesome, just a little bit tightly integrated. And then there's also HDFS on Mesos as well. And we'll talk about that in a little bit because some of this reactive distributed stuff gets really cool soon. I promise. Just got to get through the intros. So there's HDFS on framework on Mesos, so you can run that as well. And I'm a big proponent of running everything on Mesos, if that's not obvious. Again, didn't want to turn this into a Mesos talk, but I figure since we're talking about it, everything should be run on Mesos. All right, so let's get back to the real-time distributed and reactive systems. All right, so back to this diagram. So hopefully you can kind of see and think a little bit more now how this might operate, right? Because you don't just have one producer that's just sitting there, right? You have literally tens of thousands of producers that are launched in your cluster. Being able to handle different type of traffic coming in and then connect to all these different brokers that are also running within your cluster. And same thing with a complex event processing system. All of these are also running on your cluster, right? You're basically taking your producers, Kafka, Storm, or however else you're doing your complex event processing system and saying, hey, I need 300 CPUs and 2 terabytes of RAM to run this system. And you click a button, and the whole thing spins up and runs. It's pretty nifty. All right, so where does Accumulo fit in? So Accumulo fits in a couple of different places, and it actually makes for a very cool, unique solution when handling this type of request response infrastructure. So first is iterators, right? Iterators are awesome. It's very cool to have a real-time processing system in your database. And if you think about some of the other complex event processing that you might have, Accumulo could actually do that just by building iterators, right? So you could actually have a consumer or a bunch of consumers writing to Accumulo, and when they're all done, have another consumer just do a read, and that would facilitate the entire, stream processing workflow. That's a possibility. The multi-HDFS volume support is also pretty exciting too. So how many people in here use multi-HDFS volume support in Accumulo? Nobody. 2 people, 6 people. Okay. And 30 who can't raise their hands. That's fine. So with the multi-HDFS volume support in Accumulo, this is actually a very exciting use case for this type of system because in your reactive system, someone might actually be asking for data that is in an HDFS cluster that's running on Mesos that's actually spun down. So think about that for a second, right? You don't always have to have all of your data nodes running just that simple, right? If you have data from 2006 or 2007 and it's not being used all the time, there's no reason to use the compute resources, right? It's kind of like cold storage, but way better. So you could actually, in Mesos, spin down the HDFS cluster, and then when a request for it comes in, call Mesos and actually spin up the HDFS data nodes, attach the volume to Accumulo, do your scan, get the data you need from 2006, spin back down your cluster, and save all of that computational CPU and RAM and let other people use it. So cold storage isn't the right name for it. I don't think anyone's really named this use case yet, but people are using it, and it's a pretty good one. And the story with Accumulo is really the best because just being able to spin up 10 years worth of data in 3 different clusters and just attach it to Accumulo and do a scan is pretty simple. Streaming large blobs, I really like personally how Accumulo works when it comes to a file system. So if that data that's coming in and that producer is actually files, you don't want to write files to Kafka, but you can write them to Accumulo. And then in the post-processing stage in your CEP, you can read the files from Accumulo, do whatever processing you need to do, and you're good to go. So are there any questions? Yep. 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 Sure. Yeah. So the question was, if you have all these hundreds of services doing all these processing, and then you have scenarios where maybe some services are slow, right? Yeah. So it really kind of depends on the use case that you're building, because if it's a compliance system, right, you may want to wait around for the service to finish. Otherwise, your default might just be fail, right? So you may have built the system so that it always fails until everyone says okay. So it really depends on the use case. I know one security company who does this in Go, that's what they do, right? So, but it depends, right? It all depends on the use case, right? Sometimes it's okay, you can get back to it later, right? And you can put it into a queue for it to, run analysis and send an email saying, hey, there's something wrong here, whatever your use case is. But it depends. And it also depends what language you build it in as well. Because different languages are going to have different ways to do those type of timeouts, either easily or not, right? Yep. Yep. Yes. Yeah.
Write incoming data into Accumulo and then constantly scan it with the reader that does the actual event processing.
Yeah, so the question is, where is the actual integration with Accumulo? Are you using Accumulo as the event processing system, or how does that work? That was your question, right? Okay, cool. Yeah, so let's go back to the diagram. Yes and no. So I think that fundamentally, theoretically, Accumulo could do all of that. But in practice, that's not how I've seen it used. Most folks will run some other system like Storm to do the task parallelization and have the different steps and the different topologies. So I think ultimately, you need to have some consumer and some software that you write that's going to be able to run these different type of tasks, whether you build it yourself or use some other software program. That's fine, but the data store and how all that is, running behind it is all Accumulo. So it's part of the complex event processing system. In theory, it could be all of it, but in practice, it's just the data store portion. So the producers might, like in a file scenario, let's say in a scenario where you're trying to stop people from, uploading source code from, sending it to their Gmail or whatever, right? This producer is going to get that attachment, save it to Accumulo, send the event into the cluster. Some consumer can read the data, make whatever compliance checks it needs and wants on it, and then make the RPC call back. No one asked the question, how does it know where to get the RPC call back? But that's okay. I will tell you anyway. So, part of the message has that data, right? So the message has the data. So if you have thousands of producers, you don't know which server to send it back to, the message will tell you that. And there's all sorts of cool stuff that you can do with load balancing and data center replication to get pretty fancy here. Any other questions? Got 4 minutes. Anyone? Yep. Then you. Yep. So Kafka default max message size is like a megabyte. You're really not going to get great throughput if you do that more. So Kafka has a sync lock, like literally like a synchronization on writing to every partition. So in order to guarantee sequential ordering for each partition, we basically block the writer. So if you're writing large files, you're going to be holding that lock for a long time, and you're just going to suffer performance degradations. So, I mean, people do it, right? I mean, people do write like 50, 60 megabyte files to Kafka, and they're okay with it. But there's faster ways to do that. Kafka is good from like 100 bytes up until like 600,000. It excels at that, and then it just starts to slowly degrade because that's not what it's built for. Yep.
So how is this not like yarn? It looks an awful lot like yarn.
Well, let's talk about it after. That's a Mesa's question. I guess one of the biggest differences is that the actual scheduling and resource management is run and isolated by the different applications. Plus the whole C groups. We can talk about this later. I don't want to get into the whole yarn versus Mesa discussion. That's up for MapR to put another video on about it. Later. We'll have a grudge match. We'll get like a ring. It'll be awesome. Yeah.
And the Kafka consumers are poll only.
Uh-huh.
So does that mean they're polling the whole time?
Yeah, so it means they're polling the whole time. And no, it doesn't slow it down. That's always the next question that comes. So the question is, the Kafka consumers are polling all the time? And the answer is yes, they are polling all the time. But the idea is that you should always have messages coming into your Kafka consumer. And since your fetches and your polls are going essentially from memory to socket to memory, and you're only bottlenecked at your network, that is extremely fast, right? You're pulling over a megabyte at a time. Your ability to process that is way slower than your ability to pull it over the network. It's just one of those things. So it in reality, in practice, it actually is just fast enough. Yep.
Rely on the ability to replay messages from Kafka to recover from similar failures to say task goes down.
Yep. Yeah. So we have a whole thing that we've built for, like, we don't do the data center replication with Accumulo. That all comes out of Kafka as well. So the question was, do you use replay in Kafka to get data? So yes, in a whole bunch of different ways. And that's another good benefit here, is that if you need to do some other analysis, you could always go back in and scan, or just reconciliation, right? So you can run reconciliation jobs, making sure that if you have multiple data centers, that all the data has actually flowed through all the different data centers, and everything has actually been able to get to where it needs to go. And you can do that just by going back into looking to Kafka and seeing that there's a message there, and then going to some system and seeing that there isn't. Right? Pretty simple, but yeah. Yep.
So a lot of in event sourcing systems, a lot of times the producer will send a message to Kafka, and the result of all the work that's being done on the right side of your slide would actually be the result of that going back to Kafka.
Yeah. Yep.
Why the choice to do the RPC?
Sure, yeah. So that's how we used to do it. So we used to do that, and we're just saving a network step. Ultimately, right? We're eking and squeaking out another couple milliseconds of processing time, right? If you have SLAs that are in the milliseconds, every little step counts. Also, when you on the producer side, when you're consuming, doing it in a way where you're not stepping over other producers at scale becomes problematic. So if you have 10,000 producers and you've got all the responses going to one topic with 100 partitions, everyone's seeing everyone else's messages. It just slows it down. So in practice, it's okay. But in reality, as you start getting through, there's a lot of reasons where, you should write, and ultimately right before you make the RPC call, you should write to Kafka as well, asynchronously, because it should always have a copy in there. But just doing the RPC call is it's faster. It's just through experience, we've just switched it up. I think I'm out of time. Yep. All right. Thank you, everyone. Appreciate it.